It's a pretty fascinating paradox, right? Think about it. How can an AI achieve, like, superhuman transcription accuracy in a perfectly quiet, pristine lab environment, but then just completely fall apart the second it hears background chatter, clinking glasses, or a bit of a heavy accent? It's a frustrating reality of modern AI, but today's source material tackles this exact problem head-on.
The speech recognition landscape. Let's get right into where artificial speech recognition currently stands today.
To really appreciate what Whisper pulled off, we gotta look at the related works that came before it. Lately, progress in this field has been driven by unsupervised pre-training. Models like Wave-to-Vec 2.0 are really leading the charge there. Now, don't get me wrong, these prior models are incredible pieces of technology. But honestly, they're kind of like brilliant lab rats. They show amazing potential during pre-training, sure, but to actually get them to transcribe speech, they demand highly skilled, complex fine-tuning on highly curated gold standard datasets. They need their hands held. Whisper takes a totally different route. It was designed to be street smart and ready to use right out of the box, skipping that fragile fine-tuning phase altogether.
Which brings us to part 2, the brittleness problem. This is the core issue plaguing modern speech recognition models. There's this brilliant quote from the paper that hits the nail right on the head. A model that achieves superhuman performance when trained on a dataset can still make many basic errors when evaluated on another. Basically, machine learning models are shockingly good at memorizing the weird little quirks of their specific training data. So you might see so-called superhuman performance on a benchmark test, but the second you take that model out of its narrow little domain and thrust it into the unpredictable real world, it crashes and burns. It's really just an illusion of competence.
Because of this extreme brittleness, the researchers realized that if you want a genuinely robust system, the ultimate goal has to be performing well in a zero-shot setting. Now, if you're not familiar, zero-shot simply means evaluating a model on completely new, unseen datasets, without giving it any custom training or fine-tuning for that specific environment. If a system is genuinely robust, it just has to work reliably across the board, without a human constantly retraining it for every new deployment.
So, how do we get there? Let's move to part 3, the Whisper approach, and see how they solved this. To fix this brittleness, the researchers just threw out the gold standard rulebook completely. The scale we're talking about here is just wild. Before Whisper, the standard way to improve robustness was mixing high-quality datasets together. A prominent prior work called SpeechStew mixed about 5,140 hours of supervised data. But the Whisper team, they asked, what if we trade pristine data quality for massive quantity? They scaled up what's known as weak supervision to an absolutely absurd degree. We are talking 680,000 hours of audio, paired with transcripts scraped straight off the internet. That is over 100 times more data, just totally embracing the messy, noisy reality of the web. Now, obviously, you can't just feed raw internet garbage into an AI and expect magic, right? To make this messy data actually usable, they ran it through some pretty clever automated filters. First, they used language detection to make sure the spoken audio actually matched the text language. And crucially, they built heuristics to strip out what they call transcript ease. You know, those awkward, robotic, machine-generated captions that have absolutely no human punctuation. Yeah, they got rid of those. They wanted the model learning how real humans actually speak, not hallucinating based on other flawed AIs.
So the data set is completely revolutionary. Naturally, you'd probably expect the architecture behind it to be some insanely complex next-gen neural network, right? Well, actually, scratch that. The big surprise here is that there is no surprise. They used a totally standard off-the-shelf encoder-decoder transformer. The audio gets processed into a spectrogram, goes through a couple of convolution layers, and right into standard transformer blocks. And they did this very intentionally. By keeping the architecture super standard, they proved without a doubt that their massive, noisy dataset was the real game changer here, not some fancy new model design.
The real secret to making this simple architecture work so well is the multitask training format. Usually, if you want transcription, translation, and voice activity detection, you're building completely separate, highly complex systems for each one. Whisper just handles the whole shebang in a single model. It does this by converting all tasks into a sequence of special input tokens fed right into the decoder. It sees a start of transcript token, a language tag, a command to either transcribe or translate, and whether or not to include timestamps. It is incredibly elegant. You literally just feed it a sequence of commands as tokens, and it outputs exactly what you asked for.
And because of this clever token setup, Whisper is way more than just an English transcriber. It is a native multitasker and multilingual powerhouse. Out of those 680,000 hours of data, 117,000 cover 96 different non-English languages. On top of that, it includes 125,000 hours of translation data.
So what does that mean for us? It means Whisper can listen to someone speaking Spanish, French, Korean, you name it, and translate it directly into English text in one single step, all while predicting the exact timestamps. It's literally like having a universal translator right in your pocket.
All right, part 4, crushing the competition. Let's see how this massive street-smart model actually holds up against the finely tuned lab rats.
This data gets right to the heart of the brittleness problem we talked about earlier. If we compare a fine-tuned Wave2Vec 2.0 model against a zero-shot Whisper model on a standard lab benchmark like LibreSpeech, they actually tie. They perform almost identically well. But remember, that's strictly in distribution. The real test is zero-shot robustness across 12 unseen, diverse, real-world datasets. And here the results are just staggering. Whisper achieves an average relative error reduction of over 55%. It literally makes fewer than half the mistakes of the traditional model the second you take it out of the lab.
To put that into a real-world perspective, let's go back to that noisy pub scenario we started with. Check out the pub noise graph. As you move left on that horizontal axis, the background noise is getting much louder. Now, watch what happens to the traditional models, the vertical lines. As the noise gets intense, dipping below 10 decibels, their error rates absolutely explode. They completely crash and burn. But then look at the red stars, which represent Whisper. It survives the chaos. It maintains a dramatically lower error rate, even when the ambient chatter and background noise are just deafening.
So here's the absolute crucial takeaway. By actively embracing the messy, noisy reality of the internet instead of running away from it, this team built something incredible. When you evaluate the best Whisper models on long-form transcription tasks against actual professional human transcribers, it practically closes the gap. It essentially matches the accuracy and, crucially, the out-of-the-box robustness of a highly skilled human listening to an audio file.
Finally, part 5, the future of voice. Let's zoom out a bit and look at the big picture.
The researchers didn't just build one model here. They built a whole suite of them, scaling all the way from 39 million parameters up to a massive 1.5 billion. And as the data clearly shows, when they scaled that model size up, zero-shot performance consistently and reliably improved across the board. Speech recognition, translation, language identification, the works. It proves there is just immense untapped potential in simply scaling up weekly supervised learning. Basically, the more compute and messy data you throw at a simple architecture, the smarter and more robust it gets.